Hello, my name is Divyanshu. I am currently in my third year pursuing a major in computer science and engineering at Bellore Institute of Technology, Vellore. The topic I'll be presenting today is homomorphic encryption, which is a part of cryptography and network security course that I am currently undertaking under the guidance of Professor Somasundaram. Today, we will go through the fascinating and increasingly critical world of homomorphic encryption and its close ties with secure computation. So, wouldn't it be nice if we could be able to encrypt our data and send it to the cloud so that our privacy is protected? But in this case, the cloud will not be able to perform search, short, or even could run any algorithms from our data. So, this won't help us in any case. So, for this scenario, we can use homomorphic encryption. Let's see how. So, take an example. This is my hostel room's data, like my hostel room to my hometown's path. I want to store it in cloud, but I don't want it to be directly shared on the cloud because I want this information to be private. So, what can I do? Let's see with the help of an animation. So, my data will be encrypted and then a ciphertext will be stored on the cloud. Constructing homomorphic encryption. We now enter the constructive part of the presentation. The goal is to build homomorphic schemes that support arbitrary computation on encrypted data. Privacy homomorphism. The privacy homomorphism are encryption schemes that preserve certain operations. RSA supports multiplication homomorphism like examples with the help of mod we use to generate ciphertext as we have seen in the uh, startings of the course. Morphic encryption scheme. Algamel multiplicative over Z filer, which was introduced in 1999, is an additive over Z, and Yog DGN, which was introduced in 2006, supports one multiplicative and multiplicative addition. Homomorphic encryption. Homomorphic encryption is the ideal structure. Let's see how the plain text is generated. Let's define our target, such as plain space, which are the binary values, cipher space, which is a ring R with addition and multiplication operation. We want EX encryption of x1 and encryption of x2, and finally it is stored like x1 plus x2 mod p, in this case mod 2. Then we can compute any function on these encryptions. Since every binary function is polynomial, Gantry's blueprint of encryption using ECCs to gain additive homomorphism. Embedded ECC in a ring supports multiplicative operation, and bootstrapping refreshes ciphertext to reduce noise. Encryption from linear ECCs. Encryption encodes bits using error correcting codes such as secret key, good basis for the code, then public key, which is a bad basis indistinguishable from the random. Encryption 0, a word close to the code, and encryption 1, a random word far away from the code. Then modulo P encoding. The code words are the multiples of P, public key, which is called N, which can be derived from P cross Q, and a noisy multiples x1 is equal to P cross Q plus R. Then alternative encoding via distance. Another approach is use distance from the code as the coded bit, even alternative encoding via distance. Another approach is to use from the code as encoded bit. Even distance can be done by encryptions of 0 and odd distance by encryption of 1. Decryption can be given by C mod P and whole mod 2. If C is co-prime with 2, ciphertext of 0 and 1 are indistinguishable. This representation works well in lattice-based schemes. Now, moving forward to additive homomorphism detail. When C1 and C2 are added, C1 plus C2 gives the code word C1 plus. Moving forward is additive homomorphism detail. When C1 and C2 are added, C1 plus C2 gives the code word 1 plus the code word 2. If noise is small, sum remains close to the code. Hence, we can recover B XOR B2 from the resulting cipher. So this gives the distance. Addition works cleanly while error remains within correctable limits. Now, moving along, we have multiplication in ring R. For multiplication, C1 cross C2 gives the polynomial of degree 2 in the range R, B. If code is in ideal R and product of noise remains small, we get encryption B with XOR operation raised to the power B2. Thus, the encryption is multiplicatively homomorphic under careful noise control. Moving forward, we have polynomial rings. Let R be in the range of zx divided by the function fx. For example, fx is equal to x raised to the power n plus 1. Let's see the example. This is, I have mentioned one example, fx is equal to x, n raised to the power n plus 1. C is an ideal generated by gx. Encryption is given by adding small noise to gx and hx. R forms a lattice structure where noise can be bounded. Can evaluate polynomial of degree of order of t log n, where t is equal to bits in gx. Polynomial rings. Ideal lattice and BDD hardness. BDD stands for bounded distance decoding. Given x close to the lattice, let's find the distance of the lattice. Matrix ring. Additive construction. R is the matrix ring over ZQ. Encryption space is lower rank matrix mod Q and secret key T such that TA is given by 0 mod Q. Supports limited homomorphic evaluation such as quadratic form. So the problem is left ideal but not right ideal. Still can be evaluated in quadratic formulas. Dealing with errors. Security based on LWE. Given A and B, such as AX plus E, with small error, recover X. Hardness of this underpins lattice based encryption. LWE is worst case hard of all lattice under quantum reduction, offering strong post quantum security. Moving on to bootstrapping. Bootstrapping is a key innovation in Gantry's scheme. It removes accumulated noise by homomorphically evaluating the decryption circuit. Requires that encryption scheme can handle its own decryption circuit and enable circular security. Decrypting squashing. Gantries reduce the depth of encryption in circuit using sparse vectors. This enabled bootstrapping even without limiting initial capabilities. Part 2, which is homomorphic encryption versus secure computation. Now we shift to secure computation, where two parties compute a function without revealing their input. We will explore the secure function evaluation F and connection to HE. So, secure function evaluation. Suppose we have a client Alice who has data X and server Bob who has function F. And Alice wants to learn fx without telling Bob that what x is. Bob may not want Alice to know f, the function. The client Alice may also want server Bob to do most of the work, like computing of fx. Two meshes SFE. This is also called Yau's-Garrald circuit. In Yao protocol, Alice send an encoded input. Bob evaluate a garbled circuit and returns the result. Efficient for and it is efficient for small inputs, but client side cost scale with input length and function complexity. Let's recap the properties of homomorphic encryption. Homomorphic encryption has semantic security, compactness, which means cipher text size is independent of the function size, function privacy, which is optional, supports arbitrary function if fully homomorphic, trivial but useless methods. Evaluating F and C will give FC. Decrypting F and C will give function decryption of C. This fails both function privacy and compactness. It's insecure and inefficient. From homomorphic encryption to SFE. Using homomorphic encryption, Alice encrypts X, which is encryption of X will give the cipher C. Bob evaluates the cipher C, and then Alice decrypts the cipher C to get FX. No function is revealed to Alice, and Bob never sees X. So this was the case that we wanted. From SFE to HE. By simulating homomorphic encryption via two-message SFE, Alice sent encryption X, Bob replies with eval of F and C, requires public key encryption layer for completeness. Other construction. By chaining private one-hop homomorphic encryption added with compact one-hop homomorphic encryption gives multi-hop compact private homomorphic encryption. Some schemes build directly from Yau's garbled circuit for efficiency. Let's see the summary. The key takeaways are homomorphic encryption enables computing over encrypted data. Gantry's FHE, built from ECC in rings, security relies on hard lattice problem like LWE. SFE and HE solve similar problem via different models, interactive and non-interactive. So, this was the presentation about homomorphic encryption. I hope you like my presentation. Thank you.